Associate Professor of Medicine at University of Toronto, and I'm going to be speaking today about peritoneal dialysis solutions. These are my disclosures. When we look at current peritoneal dialysis solutions, the real distinction is between those that are glucose-based and those that are non-glucose-based. With regards to glucose-based solutions, there are conventional peritoneal dialysis solutions, as well as those which are low glucose degradation product and neutral pH solutions. In the non-glucose-based solution categories, we have glucose-based polymers, of which icodextrin is used clinically, as well as amino acid-based peritoneal dialysis solutions. Let's focus on conventional glucose-based peritoneal dialysis solutions. The typical composition of conventional peritoneal dialysis solutions have a sodium of 132 millimoles per liter, chloride of 101.75. The buffer is lactate, which gets converted by the body into bicarbonate and is either 35 or 40 millimoles per liter. Calcium concentrations may vary to regular calcium of 1.25 millimoles per liter or a high calcium of 1.75, and the magnesium is 0.75, and the pH of these peritoneal dialysis solutions is 5.2, which also may account for the infusion pain that some patients may experience upon their initial infusion, but the pH rapidly neutralizes upon entrance into the peritoneal cavity, but the initial pH is 5.2. The composition of peritoneal dialysate osmolality is as follows. A 0.5% dextrose solution is 22.5 millimoles per liter, or 296 milliosmoles per liter, and is hypotonic, meaning that upon instillation, the patient will have absorption of fluid from the onset. A 1.5% dextrose solution corresponds to 76 millimoles per liter and 347 milliosmoles per liter. 2.5% is 125 millimoles or 397 milliosmoles, and 4.25% is 214 millimoles per liter or 485 milliosmoles. And so the last two are extremely hypertonic solutions. It's important that if you practice in other countries besides North America, the reference may be different to the glucose concentrations. And so this is including glucose with its hydration shell, but 1.5% is also a 1.36% solution. That's the same thing. 2.5 is also referred to as a 2.27% solution if we're considering anhydrous glucose, and a 4.25% has been referred to as a 3.86% solution. So those are synonymous with each other. Note with glucose is that when one looks at the impact of glucose on the peritoneal membrane, using the three-pore model of peritoneal membrane function, you can see here that sodium and water will move according to a gradient from the peritoneal capillary to dialysate in response to the osmotic gradient that's established and the pressure difference across the peritoneal membrane. But similarly, that will also induce free water movement across the aquaporins. So one of the consequences of using glucose-based solutions is you have not only salt and water removal, but you do have some degree of excess water removal without salt. And that can create a situation called sodium sieving. The clinical correlate of that is that if patients lose an excess of water relative to salt, they may become hypernatremic, and that may stimulate thirst. That may happen particularly with higher glucose concentrations, and as well may happen with more frequent exchanges, and that's a clinical concern that one has to have. What are some of the considerations using glucose-based PD solutions? One of the things, as we realized, there's absorption of glucose across the peritoneal membrane. And what does this lead to? Well, this may lead to metabolic consequences. So the excess glucose absorption may lead to weight gain, may lead to challenges with glycemic control in diabetics, and may lead to lipid profile abnormalities. As well, particularly with long exchanges and with a lower glucose concentration, there may be diminished ultrafiltration, which may be a concern during the long dwells with low glucose concentrations. In addition, long-term glucose exposure to the peritoneal membrane has been one of the potential contributors to some of the deleterious longitudinal structural and functional changes that we know happen over time on peritoneal dialysis to the peritoneal membrane. Moving on to low glucose degradation product neutral pH solutions. How are low glucose degradation product solutions produced? Well, it's important to know that when conventional PD solutions are produced, they're under conditions of heat sterilization, and that leads to glucose degradation products which are formed both during production and storage. By producing peritoneal dialysis solutions in an extremely low pH environment, that avoids the caramelization of glucose and avoids the production of GDPs. So a dual chamber, by allowing the glucose to be produced and stored in a very low pH compartment at 2.8, will separate the glucose from catalyzing substance and will allow for a solution to be produced that has reduced glucose degradation products both in production and storage. When you look at glucose degradation products, this is the process by which glucose gets converted. Glucose may be directly converted into glucose degradation products, as depicted in the top right reactions. In addition, there may be immediate reactants that are formed. And so glucose degradation products may have multiple steps from glucose or may directly be formed from the breakdown products of glucose. If you look at the glucose degradation products themselves, they've been implicated in peritoneal membrane toxicities. And there has been several studies that have looked at the impact of GDPs on the peritoneal membrane, both from cell culture studies and animal studies, as well as human studies looking at the changes in peritoneal biomarkers such as cancer antigen 125, all demonstrating that glucose degradation products may be part of the progressive injury that we see with the peritoneal membrane over time. There's also been research that has pointed to potential renal toxicity of glucose degradation products, particularly to tubular epithelial cells. And in addition, the pH of PD fluid may also influence the peritoneal membrane and host defenses. Many low glucose degradation product PD solutions do also have a neutral pH accompanying with them. Slide here shows you the commercially available low GDP solutions. Now, the only one that's not commercially available right now is the Gambersol solution, which has been discontinued. But you can look at all of these solutions have similar properties, and what you can see is that glucose is separated from the bicarbonate and the buffer. And that's really important because the bicarbonate is kept separate from the calcium to prevent precipitation, which allows for bicarbonate-containing PD solutions, and as well, it allows the glucose to be stored in a very low pH compartment, which again allows for these dual chamber PD solutions allow for this to take place.